Great, thanks, Kara. Hello, everybody. Again, my name is Chris Smith. Today, we'll be kind of taking a journey from a problem to a solution, and we're going to be thinking about how to kind of unveil innovation pathways using graph analytics. We'll be talking primarily about research data and trying to hone in on kind of some indicators of where the technology landscape might be going in the future. A quick agenda. Again, I'll just go through an introduction, talk about what I do day to day and what I enjoy doing. Then we'll quickly define the problem. We'll talk about the solution a little bit, and then we'll get right into the outcomes, and we'll see some cool data visualizations and talk about kind of how we think about the solutions that we've created. So again, Chris Smith. I'm a software engineer at Thomson Reuters Special Services. Thomson Reuters Special Services is a subsidiary of Thomson Reuters. We primarily think about helping our clients solve problems with our data and their data and build kind of rapid solutions that help them advance the mission. I sit in an interesting nexus of data science, engineering, and consulting. So I spend a lot of time working with our clients to understand their problems and then also building solutions for them as well. Before TRSS, I worked in a little bit of both private and public sector. So I've kind of seen a decent bit in my short career, and I've used a lot of graph analysis to kind of help bring solutions to bear. And I enjoy building cool things. Again, use Neo4j a lot, but also a lot of graph technology. And I see a ton of value in using it to convey complex ideas, but also do some really interesting analysis. So the problem that we're kind of taking a look at is, customers really want to understand where to focus their time as the technology landscape evolves. As we all know, this is something that we've seen even in the past year, right? These huge jumps in technology innovations that come seemingly out of nowhere. But can we use data and some analytics to help our customers understand these problems? So we'll kind of outline a few customer questions, and we'll come back to these once we've kind of built our solution. We've gone on the journey together, and we'll provide some outcomes for these. So a question might be, what does innovation look like in a given country? So some answers we can provide there are looking at geographic innovation hubs, right? Like where are the influential universities throughout a given country? We can look at output for a country. So this is the number of academic papers that are coming out in given topics. We can also look at citations, right? How much traction are these documents getting out in the academic community? And we can also look at patents. So once the research is out there, entities are going to take the opportunity to kind of lock down that IP. So we can also look at that data as well to provide interesting insights on this question. So that's kind of the macro level. So let's go one level deeper. And a question a client might ask once we've given them that is, we've kind of honed in on a university, and then they ask, what technology is a university focusing on? So we want to kind of bring the data to the table that allows them to look at research topics, leading researchers, influential researchers in the given research areas, and then also, start to define maybe some custom research communities that give us some novel insight to answer these client questions as well. And kind of at the most micro level, we have, all right, we've identified a university, we're in a country that we're interested in, but now, we're looking at specific researchers. And one of the more interesting questions that we'll try to answer today and in the future is, who will a researcher collaborate with next? And some of the things that we can provide there to help answer that question are things like collaboration networks. So co-author relationships, who are these people collaborating with? But then also kind of looking at cross-community collaboration. So you have a researcher in this community, a researcher in this community, they start collaborating. That might be a signal that there's some innovation coming from those two researchers in a new area that we might want to focus on. So our solution that we're going to try to walk through today is pretty simple, right? We've got we're going to ingest some entity resolved data into Neo4j with graph analytics baked directly into that graph. So when at query time, all those analytics are ready to go for our users. So we're gonna, like I said, we're gonna start in Snowflake, and we're gonna be kind of a downstream of an entity resolution process that's going to merge together a couple different data sets that we'll talk about later. But this is going to give us kind of these nice, clean, golden records that we don't have to do much data engineering to with, and then we'll pull those into Neo4j. Once that data is inside of Neo4j, we're going to use kind of the out-of-box tooling that is given to us in Neo4j Graph Data Science library to write those analytics using the structure of the graph to provide novel insights when possible. We're going to place a fast API interface in front of that Neo4j database. And why? Well, it's really important in the line of work that I'm in, particularly to build out solutions for kind of two different parties. You have your developers who are going to come to the table with really cool applications, maybe even new data that they want to be able to marry up with your application. So we want to give them the ability to do that. So the Fast API is really focused on that developer experience, allowing them to interface with our data with little to no effort. They don't have to write any cipher or anything. The other kind of audience that we're going to be building out a solution for is our analysts, right? People who want those answers really quickly because they need to make a decision with this data, or it's going to go into a bigger report and they just need an answer quickly. So we're going to also have kind of a user interface that we're going to get some answers from later on in the presentation. Two things to note here. So these blue arrows are automated with GitHub Actions. So the nice thing about GitHub Actions and automating these processes with that is that with kind of a press of a button, we can both ingest our data from Snowflake into Neo4j relatively efficiently, and we'll dive into that a little bit. And we can also rewrite our analytics to the database as well in an automated fashion as we're adding new analytic modules to the code base. So one of the most challenging things when we start this journey, we have an idea, but we have our data, but one of the most important steps in any kind of graph database solution is identifying what you want your schema to look like. And in kind of this rapid prototype, rapid solution world, we always have to answer the question, how do we move from schema idea to implementation quickly? So we'll walk through kind of a toy example here to build a foundation for the rest of our solution and some intuition about kind of how we're modeling our data. So here we have a really simple toy example. We have a source label, source type, destination label, destination type, and a predicate. So these are triples, right? And these represent nodes and edges that ultimately will end up in our graph database. So how do we go about kind of formulating our schema from this flat data? Well, if we look at that source type and destination type column, we can kind of start to identify what our node types will be. We've got Chris, who is a person. We've got Mercier University, that's an organization. And we've got a new technology announcement, which is a piece of news. And we've got the Nodes 2023 paper, which is an academic paper. So great. We kind of have our entities defined, but how are they going to be connected in our graph database? That's where predicates come in. So we have two different predicate types there, which represent the edges between the nodes that we just identified. So we've kind of taken our intuition on this flat data, and we'll quickly kind of draw this toy model, this toy graph data schema. So intuitively, we have a person that is an author of an academic paper, like we just said. We have a person that is affiliated with an organization. And maybe, we have some upstream NLP process that's able to look at news and then affiliate that news article with the organization mentioned in it. So we have that organization affiliated with news relationship. Okay, great. This is still just an idea though, right? We haven't really codified it. And when we do move to code, we want to make sure that it's highly reproducible code, something that a developer can get in there and extend. So how do we do that? Well, one of the great tools out there that helps us think about this is NeoModel, right? So that's an object relational mapper. It's really intuitive to kind of help you build out this graph schema inside of a Python code base. So let's walk through that implementation really quickly. So NeoModel is going to give you this out-of-the-box structured node class, and we'll keep it simple. We'll just implement kind of a high-level, a parent graph node that's going to be the parent node of our child classes that we're actually going to implement inside of the graph. So off of that graph node, we have a news node that we'll codify inside of NeoModel. Same idea with our academic paper node and organization and person. So great, we have this kind of simple mental model of how we're going to do this. Let's check out the code to actually do it inside of NeoModel. So the great thing about NeoModel is in a few lines of code, right in a couple objects, you have your graph data schema that you can implement inside of Neo4j. So at the top there, we have that structured relationship, and this is just going to be kind of our general use relationship object that we'll use to connect our structured node classes. As you look at the graph node class, this is what's so great about kind of that object inheritance model that we just built, is if we know we have properties like a label, like a unique identifier that are going to be carried down into all of our node types, we can pack that into that parent class there, and then just inherit those properties downstream when we implement news, academic paper, person, and organization. Last thing I'll mention here is kind of how expressive creating relationships are in NeoModel as well, right? If we look at those affiliated with relationships on the person and organization node, they're really clean to write, right? They're expressive and they're easy to follow. So if a developer picks up this code, they're able to see, okay, well, I know exactly what this person's doing. It's intuitive, and I can work on this. So moving on to ingest, right? We've built our schema. Now we're going to ingest the data. So we have two specific data types here. We have academic research and news events. We have an entity resolution process that's going to kind of marry those two up, create a bigger version of the table we just looked at. And that's going to generate about 9 million nodes and 13 million edges. We're leveraging some tooling inside of Snowpark and PyNeo to get our ingestion process down to about 25 minutes, right? It's not a Ferrari, it's not a Toyota Camry, maybe it's like a Lexus, right? We're kind of right in the middle. We could take on maybe some bigger ETL frameworks, but for right now, what we're doing works just fine. And it runs monthly or manually using GitHub Actions. One thing I'll say here is RIP to PyNeo. I'm sure a lot of people on the phone have used it. It's been recently deprecated. It was an absolute joy to use. I'm going to miss it. We'll have to translate some of this work up to NeoModel in the sprints to come. So let's dive into ingest real quick. And again, our objective here is to get from point A to point B without cumbersome tooling. And how we're doing that is we're taking our load jobs and we're kind of wrapping them inside of a GitHub action runner, which is a Docker container. From there, we use the Snowpark Python API to kind of lazily execute a big query against our Snowflake instance. And then we call 10,000 row batches into those load jobs that are running in a parallel fashion inside of our GitHub action runner. So what that allows us to do is on the other side of that, when we're pushing the data to Neo4j, we're actually pushing 10,000 rows in parallel. And that's how we get that semi-fast 25-minute-ish load time. And this is all, again, this is all done inside of GitHub Actions right now. So the most important part of this is the analysis of the data that we're ultimately going to be looking at. And what, again, we're really focusing on is using the structure of the graph to drive novel insights. Some of that data that we're entity resolving, it's going to have some analytics baked in. but we want to use the structure of the graph that we're creating using our entity resolution process to create novel insights that maybe not everybody has access to, right? And that's super valuable. And I think this is applicable to any workflow that has that ability to translate multiple data sets into a graph, and then bake the analytics directly on top of it. Some of the ideas that we think about for this project and others are listed here, and we'll kind of walk through how intuitively we think about them. So first thing, always looking for influential entities, organizations, academic researchers, news events that have a lot of technology mentioned in them. We want to be able to bubble those up quickly in our downstream use cases, and we use PageRank to do that. It's an efficient algorithm, it's well understood, and it's also conveniently wrapped inside of the Graph Data Science library. All of the things that we'll be looking at today are. The second thing on the slide here is, similar entities. For clients, they're very focused on an organization perhaps, right? But going that second level and being able to show them, hey, you're interested in this organization, but this organization is extremely similar to it. Maybe they should be on your radar as well. And that kind of similarity metric in the Jacquard similarity captures that for us. We also want to create our own kind of custom defined communities of interest. So we have, researchers that are writing papers that are affiliated with an organization. That presents a really interesting big graph that we can start to place custom communities on using things like Louvain community detection to do so. This hidden relationships piece kind of gets us into the realm of thinking about how we are going to unveil innovation pathways, so we call them, right? And this is going to be able to tell us, should these two things be connected? In the case that we're looking at, being able to assign some probability that these authors that are contributing on different lines of work or effort inside of our graph, there's some probability that they should be connected is extremely interesting for us. And again, is kind of packaging up those novel insights explicitly in that edge we're able to create. So we have a still very experimental logistic regression pipeline, link prediction pipeline that we're working on that we'll see some examples of later on in the presentation. So we're all familiar with this problem that I'm about to talk about, right? And that is, how do we package up cool analysis that a data scientist might be doing inside of a Jupyter notebook, or up in kind of maybe a not as clean code base? How do we package that up and give it to our software developers as kind of this modular, reusable component to generate analytics graph-wide? One way to think about this is just isolating that functionality into its own object, like we see here in this PageRank example. So this PageRank class really just inherits that graph projection service. That graph projection service is just taking care of some of the graph projection. It has some utility functions in there that we've written, but then if you look at the kind of bread and butter of this class, it's in that create function. And this create function is going to do three things. It's going to check for an existing subgraph. If that subgraph exists, we're going to drop it. And then we're going to create that subgraph that we're going to calculate our metrics on top of using the project API. And then we're going to actually calculate that PageRank metric onto our graph and write those analytics directly to that subgraph that we've created earlier in the function. And then we're going to clean up and drop that graph. So great, we've kind of packaged up our analytic. It looks great, it looks super reusable. You could probably use this on any Neo4j Graph database, but how are we going to implement that inside of a pipeline that's going to generate those analytics in that GitHub runner infrastructure that we talked about earlier? So one really easy way to do it, and the way we're doing it right now, is build a command line interface for these analytic services, these analytic objects, to run inside of. So here you see, we're just using argparse to pass some environment variables into our connection URL. And then, in very minimal code, we're actually able to write this analytic And it gives us, again, these reusable components inside of our code base that we're able to use kind of across different projects. So if you look in our code base, right, we've got kind of all of our analytics packaged up like this, and we're free to use it in other places as well, which is a nice utility. Last kind of piece of infrastructure we'll talk about is this REST API. And again, we're using Fast API and Neo model to get the job done here. And the core concept of this is we want to abstract any complex cipher or queries out for developers so they can just hit these endpoints and get the data that they need. So some of the functionality we've implemented is shortest path, creating subgraphs, and searching for top-end similar nodes. We're also providing a full text search functionality, and that's using the Lucene index that's built directly into Neo4j. Lastly, and maybe interestingly, is kind of our CRUD model that we're also providing through the REST API. We're actually using an in-house Pydantic Neo model integration. So this is inspired by another very good Python package called SQL model, written by the same author as Fast API. To my knowledge, there's no open source version of this, so we're kind of tracking potentially open sourcing that in the near future. So outcomes, right? Let's come back. We've kind of built the solution. We've created our schema. We've ingested the data. We've written our analytics. Now we have this big graph database that we can start to answer client problems. So let's kind of circle back and see what outcomes we can create. First, what does innovation look like in a given country? Well, the great thing is, since those entities are, entity resolved, our universities actually are going to have latitude and longitude on them. So we can take that piece of data and the page rank that we've written graph-wide to plot those geographically and provide this kind of interesting insight into where US innovation hubs or influential innovation hubs are around the world. So if you look, or in the United States. So if you look at the East Coast, right, you're seeing a big hub in Boston, that's probably MIT. And then kind of down through to Georgia, maybe that's our friends at Georgia Tech. And then if we look on the West Coast, we're seeing, the usual players, probably Berkeley, Stanford, you name it out there. The other thing we can look at is the output of a given country year to year, which is also very interesting, especially if you were to throw multiple countries up here. But in this case, we're just looking at the United States. So the things that we can do from more of a temporal aspect with this data is look at percentage change in total citations year to year. We're seeing there's a bit of a drop in 2022. We can also look at percentage change in total published works, which are, both kind of high level metrics that we can provide to answer this question. Next, right, let's focus on a university and answer the question, what technology is the university focusing on? So we'll look at Stanford University. We'll look at the research concepts, influential researchers, and research communities affiliated with Stanford. So some visualizations here. You can see, since we have those research concepts for Stanford, we can kind of look at the bar chart here, physics, engineering, computer science, quantum mechanics, all the usual players there, mathematics. But the other interesting thing that we can do is also provide influential authors by community. And how we're defining influence here is using a combination of degree and page rank to create this scatter plot that's colored by the research community that these authors are a part of. So if you're up in that kind of top right quadrant of this graph, you're killing it. You're making a huge impact on the research community. And we're able to kind of also drill down into the communities that these researchers are a part of as well, to see what research concepts are part of the communities as well. So let's take a look at that. The community analysis. So again, we're looking at the Louvain communities that we've generated on top of our graph, and then we can see some of the research topics that are actually inside of the communities, which is really interesting. So we see kind of the same things that we saw in that those top research concepts, quantum mechanics, telecommunications, nanotechnology. So not only are we able to see kind of what technologies is a university focusing on, but we're also able to look at what communities they're a part of, which influential researchers are coming from that or affiliated with that university as well. So we're kind of able to go one step further with this graph solution that we've built. And lastly, we can look at, who will a researcher collaborate with next? So in this workflow, we've started with Stanford, we've brought back some researchers. Now we're interested in, some highly influential researchers that we want to understand what their collaboration network looks like. So we're going to pick, if you look at the UI screenshot on the bottom, right, there's a list of the researchers. We've picked one researcher and we're getting two things when we click that Get Collaborators button. We're getting the known collaborators of that researcher. These are people that they've already kind of done research with, but then we're also using that logistic link prediction model to look for predicted collaborators, right? And these are people that don't have an explicit relationship in the data, but maybe they should based on some probability and the data that we have in our graph so far. And this is where we look at, if we look at kind of zoom out and think about, we look at those relationships that model is creating, we can really start to get some novel insights and kind of unveil, if you will, some of the pathways that don't yet exist. And that's something that we're constantly looking at, but we feel like we have a good understanding of the data and a great solution under our feet to start kind of going towards looking at what the future might look like for research across the globe. So like I mentioned, future work here, really want to get into the temporal collaboration networks. So we have the data to kind of look at, kind of add account for recent collaborations versus old ones. So we're really excited about kind of getting in that space and being able to, more confidently look at some of those predictive analytics we're generating. We also want to generate natural language community labels. So if we think about those communities that we generated, we want to be able to assign natural language labels so an analyst knows what they're looking at. So that's where maybe some topic modeling might happen with the research paper abstract, or even maybe some experimental LLM summarization workflows that will generate those labels in a little bit more automated fashion. And we're excited about exploring both of those areas. That concludes my talk. We went on a journey, right? We ingested some data, we created a graph schema, we wrote our analytics, and then we started answering client questions in a relatively quick manner, right? And that kind of rapid solution prototyping is the kind of thing we're always doing for our clients at Thomson Reuters Special Services. And this approach, I hope it gave you kind of a perspective on how we can go from 0 to 1 in a relatively quick manner. Thank you. I'm going to look at the Q&A real quick.